Welcome back to the Learning Den. Ready for another deep dive?
Always.
Today we're going somewhere colder than you can imagine.
Oh,
Colder than an ice planet in a sci-fi movie.
all right. I'm intrigued.
We're talking about Bose-Einstein Condensates, BECs. They're talking about temperatures so low, get this, that atoms start blurring the lines between, well, being individuals and being like one thing.
So unity, like a collective.
Yeah, exactly.
It is remarkable, to think that a group of atoms just chilling, getting slower and slower until, boom, they're not a group anymore. They become one entity. A superatom, if you will. That's a Bose-Einstein condensate, a BEC.
I like to picture it as a bunch of tiny dancers, and they suddenly realize they're all doing the exact same moves, like at the exact same time.
Yeah.
And they're like, hey, why don't we just become one giant dance move?
I love that analogy.
But how do we get these atoms to perform this, synchronized dance routine?
Well, it all starts with a very special type of particle called a boson.
Okay, bosons. Remind me about those.
Think of bosons as the social butterflies of the quantum world. These are particles like photons, the particles of light or certain types of atoms. What sets them apart is that they can all occupy the same quantum state. It's like fitting, 100 people into a phone booth. It's something that other particles, fermions, just can't do.
So bosons are the life of the party, squeezing into the same quantum space, while fermions are sticking to their personal bubbles.
Exactly.
Okay, I like it. So how do these social bosons become BECs?
Temperature, my friend. Temperature. We have to cool them down to almost absolute zero. We're talking negative 273.15 degrees Celsius.
Wow.
As we cool them down, they lose energy. And eventually, all the bosons, they fall into the lowest possible energy state, like a bunch of bouncy balls finally coming to rest at the bottom of a hill.
So they're all just piled up at the bottom of the energy hill, but they're bosons, so they don't mind getting cozy, right?
Yeah, exactly. And this is where quantum mechanics gets really, really weird. They're not just piled up. Their wave functions, which describe their quantum states, actually overlap.
Whoa.
Yeah. Imagine each boson is like a ripple in a pond. As they get colder and closer, those ripples start merging until they become one giant wave. And that, my friend, is what we call a BEC.
A giant wave of matter. Okay, now this is starting to sound less like a dance party and more like a scene from a superhero movie. But this isn't just theoretical, is it? Scientists have actually created these BECs.
They have. In 1995, Eric Cornell and Carl Wyman, along with Wolfgang Ketterl, they did it. They cooled rubidium atoms down to a fraction of a degree above absolute zero, and they observed the first BEC, a landmark achievement. It earned them a Nobel Prize in Physics in 2001.
A Nobel Prize. That tells you this is some seriously groundbreaking science. How do they actually cool atoms down to, practically absolute zero? That's colder than interstellar space.
It's a complex process, but the key is lasers. They use a technique called laser cooling, where lasers are actually used to slow down the atoms. Imagine gently pushing against someone running towards you, slowing them down with each push. That's basically what the lasers do to the atoms, sapping their energy and cooling them down.
Laser cooling. Wow. So not exactly your average refrigerator?
No.
So once they've chilled those atoms down with lasers, how do they keep them from escaping?
That's where magnetic fields come in. They use magnetic fields to create a trap, essentially, an invisible trap for the atoms. It's like creating an invisible force field that holds the atoms together.
Okay, so we have lasers slowing the atoms down. We have magnetic fields keeping them contained. What's the final step in making this superatom?
The final step is a technique called evaporative cooling.
Okay.
It's kind of like when you blow on a hot cup of coffee to cool it down. But in this case, they selectively remove the most energetic atoms from the trap, leaving the colder ones behind. This reduces the temperature even further and allows the BEC to form.
So they're basically giving the hottest atoms an escape route. So the cooler atoms can, settle into their superatom state.
That's a great way to put it.
This is starting to sound like a highly sophisticated game of atomic freeze tag. But why go through all this trouble? What makes BECs so special?
Well, EECs are so interesting because they basically give us this macroscopic window into the quantum world. We can actually see, quantum phenomena, Things like wave-particle duality happening on a scale that, we can observe with our instruments. It's kind of like a bridge between that bizarre world of quantum mechanics and the, familiar world of classical physics.
So BECs are like, what? A quantum reality show, letting us peek behind the curtain of the universe at the most fundamental level. Fascinating. But what can we actually do with these superatoms? It all sounds very science fiction, but you mentioned earlier they have some practical applications, right?
Absolutely. And one of the most mind-blowing applications is the creation of atom lasers.
Atom lasers.
Just like an optical laser emits a beam of light that's coherent, an atom laser emits a beam of matter that's coherent.
A beam of matter. Okay, now you're really making me picture a science fiction weapon, that vaporizes anything in its path. But I'm guessing that's not really the reality of atom lasers?
Not quite. While the idea of a matter beam definitely sounds like it's straight out of a sci-fi movie, atom lasers are really more about precision and control. Imagine like a stream of atoms all moving in perfect unison, like a perfectly choreographed marching band. This level of control over matter opens up just incredible possibility.
Okay, I see, yeah. With that level of precision, I can see how that could be really useful. What are some of the potential applications of atom lasers then?
Well, one application is in ultra-precise atomic clocks. So, I mean, the current atomic clocks are incredibly accurate already, but atom lasers could really take timekeeping to a whole new level. I mean, we're talking about clocks so precise that they would only lose like 1 second every few billion years.
Wow. So that makes our current timekeeping devices look like sundials.
Pretty much, yeah.
What else can we do with these incredibly precise beams of matter?
Well, atom lasers could revolutionize lithography. That's the process of creating patterns on surfaces, which is essential for making computer chips and other microelectronics.
Right.
Imagine using an atom laser to create even smaller and more powerful electronic components.
So we could be talking about even faster smartphones.
Yeah.
More powerful computers, all thanks to the synchronized dance of atoms.
Exactly.
That's pretty remarkable.
Yeah.
But you also mentioned something earlier about using BECs to simulate other quantum systems.
Right.
Can you explain that a bit more?
Of course. One of the most exciting applications of BECs is in quantum simulation. So imagine building a miniature model of a complex quantum system like, let's say, a superconductor using a BEC. We can then manipulate this model and we can study it to really understand how the real system behaves, something that's incredibly difficult to do directly.
So it's like building a tiny quantum Lego world where we can play around with different configurations and then see how they behave.
That's a great analogy.
That sounds incredibly powerful. What kind of insights could we gain from these quantum simulations?
Oh, the possibilities are vast. For instance, we could gain a deeper understanding of superconductivity.
Oh, okay.
Which is the ability of certain materials to conduct electricity with zero resistance. This could lead to incredible technological advancements, things like lossless power transmission or super efficient computers.
Zero resistance. That's like the holy grail of energy efficiency.
It is.
What other mysteries could BECs help us unravel?
Well, we could even use BECs to simulate the behavior of black holes.
Black holes?
Yeah, those enigmatic objects with, such intense gravity that not even light can escape.
So we're talking about simulating black holes in a lab.
Exactly.
That's mind-blowing. It really seems like BECs are giving us a chance to explore some of the most the most extreme and mysterious phenomena in the universe. But are there any downsides to this technology? Any challenges or, potential risks that we need to consider?
That's a great question, and it brings us to a very important point. While the potential of BECs is, enormous, there are still some significant challenges to overcome.
Okay.
One of the biggest hurdles is maintaining those ultra-low temperatures required for BECs to exist.
Right. We're talking about temperatures just a hair's breadth above absolute zero.
Exactly. It requires incredibly sophisticated equipment and a lot of energy, really, to reach and maintain these temperatures. And another challenge is just, the fragility of BECs. They're incredibly sensitive to any kind of disturbance.
So even the slightest vibration or stray magnetic field could just disrupt that, the delicate dance of those superatoms.
Precisely. So creating a stable environment for BECs, that is a major engineering challenge. And as with any, powerful technology, there are always ethical considerations. We need to think carefully about the potential implications of these technologies, especially as they become, more sophisticated and more accessible.
Yeah, that's a crucial point. It's essential that we have these conversations about the ethical implications of any new technology, but especially something as potentially transformative as BECs. So where do you see the future of BEC research heading? What are the next big breakthroughs on the horizon?
Well, that's a question that really excites scientists all over the world. One very promising area is the development of BEC-based quantum computers,
Wow.
which could really revolutionize, well, I mean, fields ranging from medicine to material science. Another exciting avenue is using BECs to really probe the fundamental laws of physics, potentially leading to new insights into the nature of, gravity, dark matter, even the origin of the universe itself.
Wow. BECs as tools to unlock the secrets of the universe itself. That's a pretty awe-inspiring thought. It seems like we've only just scratched the surface of what's possible with this remarkable state of matter. It really does sound like BECs are, I don't know, poised to become like a major player in, well, in science and technology.
Yeah.
But let's step back for a moment and think about what it all means, We've been talking about atoms behaving like waves, simulating black holes in the lab, building computers that just defy the limits of classical physics. It's almost like we're, I don't know, stepping into a science fiction novel.
It really does feel like we're kind of on the cusp of a new scientific era, where the boundaries between, science fiction and reality they're blurring. And I think it's important to remember that this revolution is being driven by, something incredibly simple. It's that desire to understand the universe at its most fundamental level.
It is a good reminder that even the most, complex, mind-boggling technologies, they often stem from just a basic curiosity about the world around us. So for our listeners who are, just starting to wrap their heads around this whole idea of BECs, what's the key takeaway? What should they be pondering as they go about their day?
I think the biggest takeaway is that the world is far stranger and more wonderful than we often realize. I mean, BECs are a perfect example of this, They show us that matter, like the stuff that makes up everything around us, can behave in ways that they defy our everyday intuition. And they challenge us to really expand our understanding of what's possible and to embrace the mysteries that still lie hidden in the universe.
It's a good reminder that the universe is full of surprises, and that the more we learn, the more we realize how much we don't know. And that's what makes science so exciting. It's a never-ending journey of discovery. And with each new discovery, like BECs, we open up new possibilities, new ways of understanding our place in the cosmos.
Beautifully said. And, who knows what other wonders are waiting for us out there. Perhaps someday, we'll be having a deep dive into a state of matter that's even more bizarre, more counterintuitive than BECs. But for now, let's just savor the wonder of these superatoms and the incredible insights they offer into the quantum world.
Indeed. Well, thanks for joining us on this deep dive into the world of Bose-Einstein condensates. We hope you've enjoyed the journey as much as we have. Until next time, keep exploring, keep learning, and, keep asking those big questions about the universe and our place within it.